So this is Donna Nelson. We're continuing with the chapter on ethers, epoxides, thiols, and sulfides. So we're here on the second video. We're going to look briefly at each of these four reactions of ethers, nomenclature of epoxides, preparation of epoxides, and enantioselective epoxidation. So ethers, the reactions, ethers can undergo acid-promoted cleavage. And so here, if you put the ether in the presence of an acid, of course, the first step is going to be protonation. And this reaction, the reaction of the ether overall is going to be to give alkyl halides. So here we have protonation, and then the halogen, the halide, is going to come in, do an SN2 reaction, a backside attack, and eliminate the alcohol. So the ether now has become the alcohol and the alkyl halide. So here's your first equivalent of the alkyl halide. Then the second equivalent of the alkyl halide is formed by another reaction that has much the same mechanism. Once again, you protonate the alcohol from the product from the first step. That creates a good leaving group here. And then X minus, the halide comes in, does a backside attack, an SN2 reaction, and you get your second alkyl halide. So this is the first type of reaction of ethers. It works well with HBr and HI because those are very good nucleophiles. If the alkyl group is tertiary, then the cleavage occurs via an SN1 mechanism. If the alkyl group is aryl or vinyl, substitution won't happen. So you're able to cleave one of these bonds, the alkyl group, but not the aryl oxygen bond. So one of your products will be phenol. Ethers can undergo auto-oxidation. You remember from the chapter on radicals. We've already discussed this, so you will have peroxides form at the position alpha to oxygen. It's a free radical mechanism. Here again, we looked at this briefly in the chapter on radicals, chapter 10. And so you have your initiation step to pluck off a hydrogen atom, H dot, and you will have a radical formed here, alpha to the oxygen. And so this is the initiation step, formation of your carbon radical. Then you're going to have a couple of propagation steps where this, the whole reaction, of course, occurs in the presence of oxygen. So the carbon radical, single electron comes in. You're going to form the carbon-oxygen bond. One electron of that two-electron bond comes from the electron on carbon. Another one comes from an electron on oxygen. So you have formed a carbon-oxygen bond. That's your first propagation step. Then your second propagation step is O dot abstracts H dot from your reactant. And so you can see that this unpaired electron moves in. You're going to form this oxygen-hydrogen bond. The other electron of that two-electron bond comes from the carbon-hydrogen bond. And so you're forming the oxygen-hydrogen bond, and you have regenerated your reactant. Remember the requirements of the propagation step. There are two requirements, and that is that the product from each step must produce the starting materials, the reactant, for the next step. So here, this is the reactant for the next step, and here, this is the reactant for the next step. The other requirement is that the propagation steps, when taken as a whole, must consume the reactants here and produce the products here. And so these two reactions taken together fulfill both of those requirements. And so these are the propagation steps. Now here you can, and this is the termination step where you have the two unpaired electrons coming together to form a single bond, and this consumes two equivalents of your radical. And so this is the coupling reaction. This is the termination step. And so this is the way of drawing in equations what I just stated previously, which is that what is the reactant in one step must be the product in the other step. So here, this is a reactant in one step. It must be the product in another one of the propagation steps. There are often more than just two propagation steps. And also, the reactants are consumed, and the product or products is or are produced. Nomenclature of epoxides. It depends on how many atoms are in the ring. If you have a 3-membered ring, it's an oxirane. If you have a 4-membered ring, which is an ether, then it's an oxetane. If you have a 5-membered ring, it's an oxalane, and a 6-membered ring is oxane. And there's no rules or anything to correlate that to make it easier to remember. Now, this is nomenclature of epoxides. These are not epoxides. This is an epoxide. So I hope that eliminates any confusion there. The 3-membered ring in which one of the atoms is oxygen is an epoxide. The 4-membered, 5-membered, 6-membered ring are not. Nomenclature of the epoxides. The way this is named is it's named as an epoxide. I'll show you on the next slide. You can have up to four different alkyl groups. The simplest one is just ethylene oxide, and epoxides are found in nature quite often. Even though they're very reactive, they are still stable enough to be able to find them in nature, in naturally occurring compounds. So here's the nomenclature. In the first method, the oxygen is treated as a side group. And so you number the longest alkyl chain, just like you always have, and you will number it in a way to give the two carbons that the oxygen is bonded to the lowest possible numbers. And so here you do have to cite the two numbers. So this is a 2,3 epoxy pentane. 2,3 epoxy pentane, because the oxygen carbon bonds are to carbons 2 and 3, and there's 5 carbons. So this will be a ethyl, methyl, and you must put them in alphabetical order. So ethyl before methyl. Ethyl is at the 3 position, methyl is at the 2 position, 3 ethyl, 2 methyl, 2,3 epoxy pentane. The other method for naming is when you use oxirane as the parent name. And this method is used less often. I've seen the first method used much more. And in this case, you simply number 1, 2, 3, and so the 2 is the carbon that bears the larger groups, and so here the one that comes earlier in the alphabet. So this is E before M. And so here, 1, 2, 3. So this is 2,2-diethyl, 3,3-dimethyl oxirane. Okay, so here you will simply alphabetize it. Epoxides can be formed when an alkene is treated with a peroxy acid. We've had that a couple of times. You will remember MCPBA and peroxyacetic acid. These are the two most common ones, and this oxygen that is attached to the hydrogen is the one that becomes the epoxide oxygen. Epoxidation is stereospecific, and this is a perfect example of stereospecificity. So you have a cis alkene converted to a cis epoxide by MCPBA, which also converts a trans alkene to a trans epoxide. So you have a pair of enantiomers that can be converted to a pair of enantiomers. So, or rather, a pair of diastereomers, which are converted to a pair of diastereomers. Sorry. And so, remember the pair and the pair and the P in stereospecific. And that will hopefully will help you remember that little rule. Epoxides are also synthesized from halohydrons, and this is a fairly simple synthesis. So notice that you have a base, which is going to deprotonate the oxygen, and you notice that you have these two groups trans to each other. So this is set up perfectly for an SN2 reaction. The trans relationship is necessary for this synthesis. So once again, hydroxide comes in, deprotonates, you have the alkoxide formed, and since this is trans to the alkoxide, you can do a backside attack and displace bromide, and that puts both bonds to oxygen on the same side of the ring, which is a requirement here. This is a very small ring. Both bonds to oxygen will have to be on the same side of the ring. So both of those syntheses of epoxides are stereospecific, so that if you have a cis alkene, it's converted to a cis epoxide, and if you have a trans alkene, it's converted to a trans epoxide. Now, enantioselective epoxidation, the methods that we discussed so far are not enantioselective. That means that you will get a racemic mixture out of either one by using either of these reactants, because there's a 50-50 chance that they're going to come in from the top and a 50-50 chance that they're going to come in from the bottom. And so neither face of the molecule is favored. However, there are some, this just states what I just said, the epoxide can form above or below the plane because the reactants can come in from above or below the plane. So in order to have only one of these enantiomers formed, you would have to have a chiral catalyst. And that has been done. That has been done. So this is the sharpless catalyst. And so this is the metal complex here. So titanium tetraisopropoxide, which reacts with either the plus or minus diethyl tartrate. This is the plus and that's the minus, and don't bother trying to correlate the plus with the configuration here. Remember, the plus tells you that the plane of polarization of polarized light is rotated in the positive direction. This plus means dextrorotatory, and this minus means levorotatory. So if this is complex with that, you're going to get one enantiomer. If this is complex with that and allowed to react, you're going to get the other enantiomer. So, and this will produce an optically active product. So this is remarkable. And Sharpless won the Nobel Prize for this work not all that long ago. Oops. Okay, so here, yes. Okay, so plus DET gives the one enantiomer, and minus DET gives the other enantiomer. And so, for example, if you have trans 2-hexene 1-ol, you can get either the plus or the minus enantiomer. So, and this is with 98% enantiomeric excess. And so that is incredibly good. This is remarkable. This is a fabulous result. Now, just notice that where the oxygen comes from is from this peroxide. Okay, that hasn't been discussed up until now, but the oxygen is coming from the peroxide. So this catalyst, this titanium catalyst, has to have a whole lot of things complexed with it. And then notice that this is good only for allyl alcohols. And so for me, just simply discussing what we have so far is sort of like talking about a black box. So I'm going to show you something that is not presented in the textbook, and I'm hoping that it clarifies things. If it does not clarify things for you, you can ignore it. But this is a diagram of the actual reaction taking place. So see, here you can see the titanium tetra propoxide, and here is titanium, and there is titanium. This is actually a dimer of the catalyst, okay? And here you can see the DET here, 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 here. So the DET has complexed to the dialkyl tartrate, the diethyl tartrate on the previous transparency. Here you can see that this is the ethyl. So this is complex to the titanium. And when this complexes to the titanium, you lose 2 of the propoxy groups. So notice that only 1, 2 of these 4 propoxy groups survive. And over here, only 1, 2 of the propoxy groups survive. Okay? This is a dimer. And so then the next thing that has to happen is you have to have the butyl peroxide complex to the titanium. And here the butyl peroxide, the T-butyl peroxide has come in and complexed to the titanium. Also, both of the oxygens are complexed to the titanium. And you've lost the proton off of the peroxide. And then the hydroxyalkene comes in and also complexes to the titanium. So this titanium is holding everything together. Let's just consider one side, because the reaction is going to take place on one side over here. And this is just going to be a spectator. Okay? And so that's why this reaction is only good if you have the hydroxyl group beta to the double bond. Okay? So let's look here. So now you have the hydroxyl group and complexed, and you have the peroxide complexed, and so this titanium is holding everything together very closely, and this diethyl tartrate, remember, it is only 1 enantiomer, and so it's going to introduce certain steric requirements for the peroxide and the alkene. And here you can see the oxygen which was bonded to hydrogen is right here, and the double bond is here. And so the oxygen comes very close to the double bond, and so the epoxide is formed here by titanium bringing these two pieces very close to each other because they're complexed with the titanium in, in the presence of this enantiomer that is also complexed to titanium. And so, titanium is a fairly large metal, and so it is possible for titanium to complex all of these things together at once, and the fact that this is just one enantiomer and the reaction is taking place in close proximity to that one enantiomer, that enables the chiral compound being formed. And to me, it helps so much to be able to see this intermediate, which is about to react. It is so helpful to see this so that I can understand what's going on. And I hoped that you would enjoy seeing this sort of puzzle solved rather than just seeing the pieces of the puzzle. You get to see it all coming together, and you get to see what is exactly responsible for the chirality in the product. Okay, so next time we will continue to look at sulfides and thiols and wrap up a few other details on epoxides.